All right. So we discussed Newton Raphson in the class on Friday, and I'm going to try showing uh, the code which finds the solution. So just to briefly review, the steps for Newton Raphson um, are first you choose a point, you guess what is the solution, then you evaluate the function at that guessed solution, which is xi. So you get the function's value yi. If yi is already less than the tolerance, then you can stop. Otherwise, you calculate the slope at xi yi. Then you take that slope, substitute here in order to get the next guess. Then you evaluate the function at the next guess. And if that is less than the tolerance, then you stop. Otherwise, you restart and then you repeat this procedure. So, someone mentioned in the class it would be fun to see the programming done in Cubase. So I'm going to show the code on the left here. This is clearing the screen. Initially, the guess is 1. Tolerance is set to 0.01. And I have to keep doing this until some condition on the loop. So we go line by line. We go say do iteration is iteration plus 1. That is, it will keep incrementing the number of iterations. So this is first iteration when we start. The function is defined as x squared minus 3x plus 2. The derivative of the function is defined, and that should be 2x minus 3. And so we say x is x minus fx over dfx, which is essentially the implementation of this formula here in step 4. Then we say print iteration number and whatever is the value of x new. I suppose I should have written x new here. And then we have if absolute of x new minus x is less than the tolerance, then I can exit. If it is not, x is equal to x new, and I keep repeating this process all over again. This is going to be looped. And then once we are outside of the loop, which means we have exited the loop, we can print approximate root is so and so, the tolerance used is so and so. If I run this, I get first iteration, approximate root is already 1. That's because I guessed starting with the root. Let's say I had the value of 1.2, then I have to take 3 iterations. Iteration 1, it guessed the value, or x new became 0.933, then it became 996, then it became 999, and it stopped when the absolute tolerance was 0.01. Another try is we know the closed form solution would be 1 and 2, so I'll go for 2.5. And let's set the absolute tolerance to 0.001. If I run this, 2.125, 0.125, 0.00015, and then the next one. So that's where it has started. Note that between 3 and 2, the difference is still less than 0.001. Sorry, greater than 0.001. That's why it did not stop. You could change the equation to something else entirely. So let's try one other function. Maybe let's make it cubic and let's put something like 3x cube plus some 40x square and maybe minus 20x minus 400. Then we get this to be 9x square plus 80x minus 20 as the derivative, and then we can run the same exact thing with, let's say, initial guess. I mean, okay, we can leave it 2.5. Let's see what it does. It found the solution to be 3.06 something. I'm going to generate a plot of this. I'll use MATLAB because I'm not sure how to do that in Cubase. I'm going to generate a plot of the function and a crossing line in MATLAB. This is how it looks like. So we have okay, so 1 0 is indeed very close to 3.06. Then there's one very close to minus 3.3, and then minus 13 point something. So I'm going to use an initial guess as minus 15 and run that. I get minus 13.06, and I'll use something, let's say minus 5, and there you go, minus 3.33. So, wow, this converged really, really fast. So what happens if I give minus 10? It goes to minus 13, it doesn't come back to minus 3. So that's the use of Newton-Raphson. This is a code in Cubase. I'll also show a demo code in Java, but this is essentially how you need to solve